So we are about to embark on the automatic transmission diagnosis prereq review. There's a lot of good information in here and a lot of topics that are referenced for the certification test that you'll be taking next week. So let's hop on in. First step in the diagnostic process for automatic transmission concerns. So for everything else, it's always been verify the concern. So it might be perform a initial inspection of the vehicle, like make sure that the headlight that doesn't work, or see if the check engine light's on, drive the vehicle and see if it has that hitch or misfire. But for an automatic transmission, they go at this in a different way. They want you to pull codes out of the vehicle immediately. So you'll go in and you'll pull any continuous memory or on-demand codes that are present. And the reason for this is that automatic transmissions will very frequently put themselves into default modes, and they're basically failure effects management modes. They try to keep the transmission from injuring itself more than it already has been. Any kind of heat or increased friction inside the transmission is going to have lots of collateral damage that go along with it. And so it's not uncommon to have a vehicle with a shift concern come in with a lack or loss of power because it's stuck in a default third or fourth gear. And so when you go and drive it, you will definitely verify a concern. It may not be the exact same concern that the customer was having. And oftentimes the temperature of the transmission and the transmission fluid is really important for these symptoms as well. So the first thing they want you to do is go in with the scan tool and either pull codes out of the PCM, or if it has a standalone TCM, you can pull codes out of that. Make sure that you record these codes because there's a good chance you'll be requested to clear the codes to see if we can get the transmission back into a normal operating state so that we can actually duplicate and verify the real symptom that has caused the transmission to go into a default mode. The technician recorded and cleared the continuous memory codes. The recording part is really important so that we know if things are being reset or if some of those continuous memory codes may have been due to past driving experiences, low battery voltage, weird things like that. Is it necessary to perform both the key on engine off and key on engine running test after we do that? And the answer to that is definitely yes. So the major difference between a key on engine off and key on engine running test are that KOEO is basically testing for electrical failures, a PID that is out of range, and all of our inputs, all of these PIDs are populated by voltages that are received by the module. So let's say we have a transmission fluid temp sensor that's setting a code. Now if the module sees that that temp sensor is showing negative 40 degrees and the intake air temperature sensor is showing 70 degrees, it does a correlation between those two codes and can realize that, okay, this doesn't make sense. So this is all done by the comprehensive component monitor that's part of our OBD2 check sheets when we do inspections, and it's for the emissions systems and government mandated and P codes and all that kind of information. But the long short is key on engine off codes almost guaranteed to be an electrical failure. That negative 40 degrees for the temperature sensor is basically an open. It's the highest value that the PID can display, and it's because the circuit has a lot of resistance in it, so the computer's going to have to think a little bit about that one. We will then perform the key on engine running test as well. This key on engine running test is going to show us things that are mostly affected by the actual functionality of our hydraulic, our electronic, our electromechanical devices that are inside the transmissions and transaxles. And what we're looking for is, does the code come up for both key on engine off and key on engine running? If it does, then it's almost guaranteed to be an electrical failure. If the code doesn't come up for key on engine off, but then when we run the key on engine running test, the code pops up, then we probably have a mechanical failure of some sort. Something's burned up, a solenoid is stuck in the on or off position, but electrically the circuit is fine. All right, so this is what they're trying to help guide you through, is this idea of how is the computer paying attention to the transmission and the management of it, and how can we interpret that information to help streamline our diagnosis and get a lot of the clutter out of the way so that we can actually drill down to the base failure of that transmission. A preliminary inspection typically involves the following. That's definitely going to be all of the above. Under hood, under vehicle, transmission fluid. So look under the hood, especially if it's a transaxle, you can see basically the whole thing there. Under the hood does it look like wiring's been damaged? Is there a squirrel nest on top? Does it look like someone's been in and tried to service the transmission in some way? And there maybe are broken bolts or things that are disconnected. Maybe sometimes when someone's just serviced a unit, it's just simply that something's unplugged, and we can fix it by visually inspecting that component and finding, okay, yeah, it's unplugged, they can plug it back in and clear codes and retest. Under the vehicle inspection, we're really looking for leaks or mechanical damage, cracked cases, things of that nature. Transmission fluid inspection. So in that case, we're looking for metal and clutch material contamination, or I guess potentially even coolant or water contamination, because it'd be frothy and pink. But the tough thing with transmission fluid inspection right now is that LV, the synthetic Ford transmission fluid, turns a grayish color. They call it gray. It looks black to me if you look at enough of it, but it turns this grayish color within a few hundred miles of brand new fluid being added to a transmission. So in that case, you can't just visually look at the transmission fluid to see if there's clutch material or if it looks burned up. It used to be with conventional fluids. If it was real black, it was burned up, and you pretty much knew. Use all of your senses. You can test for grittiness. If you rub the fluid in your fingers, can you feel metal debris? Dab it on a piece of paper. A lot of shops have test swabs where it's these little squares of paper that you can put the fluid on. Oftentimes it's used to help sell fluid exchanges to customers. And then use your sense of smell to smell the fluid and see if it smells burnt up. I guarantee you will know if the transmission is burnt up, because the fluid is so foul and so burnt smelling that it's not going to be it kind of smells burnt up, but it still smells a little bit sweet like it should. No, it'll be very obvious. Oh my gosh, this is junk. Okay? A DTC reset during the Kion engine running test. So that means that we found the code while we did that test. No vehicle harness concerns were noted in the preliminary inspection. The fluid condition appears okay. What is the next step in this process? Give you a second to read through some of the options. So we'll refer to the DTC chart in diagnosis and testing. If we get a code out of a vehicle, that's a very, very convenient method for us to find the right pathway to diagnose. That code is pointing at a specific system of our transmission. It could be electrical, it could be electrohydraulic, it could be electromechanical, it could just be hydraulic. The DTC will lead us to a pinpoint test or symptom chart that we can then go through and find the right fix, more or less, diagnose right down to the source, and then we'll fix all the collateral damage and get this thing back on the road. You verify a customer's slipping shift concern on the road test, a shift solenoid performance DTC reset in continuous memory. What do you do next? All right, so the idea that they're trying to pass to us here is the fact that the solenoid DTC is a performance-based DTC. So that really references specifically the fact that when commanded, there was not the expected change. It's not picking up an electrical issue. It's looking for a actual mechanical failure. Something's not happening. Determine which symptom and possible source is closest matched to the DTC. So sometimes you'll be directed to a symptom chart while trying to diagnose a transmission related DTC, and that's oftentimes associated with these performance ones because, yeah, the solenoid could be the failure, but it could also be the valve body / main control. It could be the case of the transmission. It could be the internal components and seals of the transmissions. So it becomes a little bit more complicated, and what they want to do is try to figure out, does this transmission need to come out to be fixed properly? And if so, how much information can I get out of it before I take it out so that when I do go through it and fix it, that I have the best potential to find the root cause of what caused any damage, so that we don't put it all back together with the same valve body, let's say, and then the thing roasts itself once again, and so then we have to do 2 internal repairs, and hopefully on that second go through we would have found that the solenoid body or the valve body was having an issue. No DTC set during the road test, but the symptom was verified and recording was made. Which of the following provide the technician the best chance for a successful diagnosis? So no code, and the symptom was verified, and you performed a recording. So what do you think? All of the above. Refer to specifications for clutch and solenoid charts. So we're going to look at this in some of the subsequent questions, but this is talking about not like, oh, the clutch should have this much clearance to it. What they're referring to is under the specifications section, you can find apply charts, which will help us figure out which clutches and which solenoids could be causing this fault. Refer to diagnosis and testing symptom chart. That makes sense. Refer to the appropriate clutch component test. That makes sense as well, because it's going to be these apply components that make our transaxles and transmissions work. This one, I'm not going to read all the way through it. They're talking about recordings, and basically what they're trying to highlight is these buttons on the IDS can help you control the way that recordings work. So data capture, the little Mickey Mouse camera looking thing, that's how we get to the point at which we actually make the recordings and get back to playback. The plot format links make it so we can change the way our PID data is displayed, and then we can set the recording times. How long does the recording last? How many seconds before we push the button does it capture for us? How many seconds after we push the button? So that's the pre and post trigger time. It's us actually hitting the trigger button. Vehicle comes in with contaminated transmission fluid. Technician A says the transmission must be overhauled, but diagnosis must continue in an attempt to determine the cause before the transmission is removed. Tech B says don't waste your time with that. Take the transmission out and fix it. Technician A in this event is the correct one, because we need to try to understand why the failure happened before we go in and replace parts. And oftentimes, if you just pull a transmission out and replace the parts, you'll find that something broke or a seal is bad, and that could very possibly be the root cause. But if it's a control issue, like a harness is damaged, maybe got melted on the exhaust, a solenoid or a valve in the valve body isn't actuating properly, then we could do this overhaul and hopefully then catch it on our test drive before too much bad stuff happened. But if we miss it, if we're not diligent and this goes back out, the customer might be on the highway and it's 10 miles to the next exit, and the car's under warranty and that just had the transmission fixed, and they're just going to get to the exit and not wait on the side of the highway for AAA to come pick them up. And that is definitely enough driving to really hurt a transmission in many cases. After a transmission is repaired, what final steps are performed? Well, we're going to clear any codes that may have been set prior to or during our repair. We're going to reset the misfire monitor, because the misfire monitor may have picked up what it perceived as misses because of transmission slips and flares and bumps and all that kind of stuff. Obviously check for leaks. We'll perform the adaptive drive, which I think there's another question about this in a second, but the adaptive drive gives the PCM or TCM time to figure out the particular characteristics of this transmission. Each transmission is going to have slightly different clutch clearances just because of manufacturing variances, and maybe techs have chosen different selectives, so it will take slightly longer on some transmissions than others for a apply event to happen. And this is measured in milliseconds, so what seems like a short time for us is actually a long time for a computer. It also can figure out things like, how much power does the engine put out at these different throttle angles. It'll even learn things to the effect of the throttle body is starting to gum up a little bit. That's going to affect the torque being produced by the engine at a certain APP voltage, which accelerator pedal is our main input for driver request and power and economy and all that kind of stuff. So you can see how these layers create a lot of nuance, and so we drive the vehicle in a specific way, which is outlined by the workshop manual, and that specific type of driving gives the computer time to make these measurements and to adapt to them. Also, the type of driving helps the transmission's control module, PCM/TCM, know that it's being driven in an adaptive cycle, and it will record the information and store it in a more meaningful kind of way. What is the purpose of the adaptive drive cycle test, and when should it be performed? Well, there we go. Anytime that the adaptive drive cycle test allows the PCM/TCM to learn operating characteristics of the transmission, should be performed after solenoid body replacement and the adaptive learn has been reset. So if we get a black box from Ford with a axle or transmission inside of it and we install that, well, that has a new solenoid body inside that transmission compared to the bad transmission that we're getting rid of. And so we need to make sure that we do that solenoid body ID reset and the adaptive drive cycle test as well. The gear ratio PID displayed is the gear the control module is requesting. The trans ratio PID is the actual output ratio measured. That's true. And so if we're trying to diagnose a failure, having the gear ratio, which is in fourth gear, we should have a 1.521 to 1 ratio. That is just the way that the transaxle is built with its planetary gear sets and all that kind of good stuff. The trans ratio PID is based off of the speed sensors, so like the turbine shaft speed sensor for the input and the output shaft speed sensor for the output. That actually measures the two speeds and does a little quick math and comes up with the actual ratio of the transmission, and they should be the same because there's no slippage on the internal of the transmission. The torque converter will do what we consider some slipping because it's a fluid coupling, but on the inside, what goes in, unless we're in neutral, something should be coming out. The following symbols for data logger. So the first one is it can be controlled, so that's just next to the PID and lets us know that if we want to output state control it, we can. When that goes to an equal sign, it means that we are currently controlling it. And an exclamation point means that the correct conditions to control that PID have not been met. A lot of times people, when they're trying to diagnose a transmission, want to make it shift into different gears using the scan tool or actuate different shift solenoids using the scan tool while in gears. The IDS and the PCM won't let you do that. You have to be in park or neutral when you're making any kind of real meaningful output state control changes. So just so you know, if you get the exclamation point, it means conditions are not right, and it could also mean that there's a failure, like you're trying to control a solenoid but it's not happening. So it could mean that, but it doesn't necessarily mean that that's the case. A line pressure test verifies the pump, the line pressure control solenoid and valve, the main regulator valve are capable. It's testing to see if they're capable of building enough pressure for the transmission to operate. Yes, that's definitely true. What transmission components can cause low line pressure? That's quite a list, and it'll change, and some of the naming will change depending on which transmission you're working on. So pay attention to that, because line pressure control solenoid used to be like the EPC, electronic pressure control solenoid. So like everything else in this industry, there's many names for the same components. Alright, so let's watch that regulator work. So the pump is really just there to create flow, and these are positive displacement pumps, so it's going to be pushing stuff out, and stuff can't backflow through it back down into the pan. A non-positive displacement pump is something more like a torque converter, where we can get slippage. So the pump spins and it creates fluid flow down to my main regulator valve, and then the main regulator valve allows pressure to be built. One, through the restrictions of the valve itself, and two, through the restrictions of the holes in the valve body and separator plate. Think about in an electrical circuit, we only get a pressure differential if I have some sort of a resistance or restriction there. So as important as the flow is, the restriction adds along with that. This pressure is then controlled by our line pressure control solenoid, and you can see I've got a spring over here on this side, and I've got a fluid tap that allows pump pressure to come into the solenoid, and it will act on the back side of this valve. On this side of the valve, you can see here the pump sends pressure out. Let's see, yeah, it comes up, the pump sends line pressure out, and it comes into 3 different spots. So that line pressure, and think about piston size and back to brakes and Pascal's law and all that kind of stuff. The pump puts fluid on one side of the valve. This line pressure control solenoid puts fluid pressure, the same fluid pressure, on the other side. And we can limit that. If I turn it off, then it's just this tiny little spring in there that's pushing back against that main regulator valve, and pump pressure will win that battle, and the valve will shift over in that way, and it will limit the amount of fluid that can flow past the valve, which will also limit the amount of line pressure that is supplied to all of my apply components and their subsequent solenoids and regulator valves. The solenoid for line pressure control can increase that pressure by allowing fluid through it, and with the help of that spring pressure, I've got the same pressure that I have on this side applied there, plus the spring, so then it wins, pushes the valve to the other side, opening up these channels more so, and allowing for more fluid and more pressure to reach my individual apply components, control units, and then the actual apply components themselves. All right, so this is just a constant act of push and pull, I guess, basically. So I've got the same pressure on both sides. Nothing's really going to happen. I increase pressure on one side, my valve moves, and pressure changes. And this is the same way that shifts will occur too. Back before electronic control for transmissions, we had a throttle valve, and we had our governor. And so as we went down the road, the governor that was attached to the output shaft of the transmission would spin faster and faster the faster the vehicle went, because the output shaft is connected to the drive shaft, to the differential, to the axles and wheels. So the faster the vehicle's moving, the faster that's spinning. The faster that's spinning, the more it would open up, and it would allow more pressure on one side of a shift valve. And these early transmissions were just 2 and 3 speed transmissions, so there wasn't like a whole lot of porting that had to go along in there. So put pressure on one side. Now if my throttle is my main input to how much work I want to get done, do I want to go fast or do I just want to go? So if I'm just putzing down the road and I have, a little bit of pressure on my throttle valve side, as the vehicle speeds up, the valve moves towards that throttle valve side because the governor is opening up more and it's allowing more pressure on its side of that valve. The valve moves over, opens up a port, 1-2 shift happens. Well, now I'm in second gear and I'm about to go up a hill and I need the engine to really work. Well, I step into the accelerator more, into the throttle more, which opens up my throttle valve more. It's either attached right directly by a cable, or in some cases it was vacuum actuated, We know how vacuum changes as we open our throttle. Less vacuum with a wide open throttle, maximum vacuum with a closed throttle. So going up a hill, I step on the accelerator pedal. That opens up that side, and now all of a sudden the pressure can increase and push back against the governor's pressure, downshifting the vehicle, allowing us to get that extra torque multiplication, and up the hill we go. All right, these are the basics of automatic transmission valving, and they're still being used today. We just have a lot more gears and some computer control to make that happen instead of mechanical devices. When must the PCM-TCM be programmed with solenoid body and strategy file? When the solenoid body or main control is replaced. Sometimes the main control will come with all the solenoids on it. Other times the solenoid body and main control are separate. So pay attention to that when you're ordering parts. Ford doesn't want you to put on a solenoid body if you don't have to, and vice versa with the main control. And like I said before, a brand new transmission comes with a brand new solenoid body, so make sure you do your ID and adaptive drive cycle after that. When stall testing a transmission, what components are being tested and what are they being checked for? Well, we're testing our brakes even though it doesn't say that, right? Because if the brakes don't work, stall testing is not really going to do us much good. So make sure that your brakes hydraulic system is working properly. If the vehicle is four-wheel drive, I often like to put it into the four-wheel drive mode because the back brakes, especially on pickup trucks, aren't really expected to do a whole lot because most people drive a pickup truck around like it's a sedan, so empty in the back, so all the weight's up front. So four-wheel drive will make it so your torque is evenly split between all four of your wheels, and you're less likely to do a little brake stand in the shop. But as we're stall testing, we're going to check the torque converter. One, if the torque converter smokes, the engine's just going to rev way up. Same thing with if our the one-way clutch, which is part of that torque converter, is smoked, it will rev way up as well. And then whatever clutches are applied in our first gear. It's not going to test all of them because we can't do a stall test when we're going 35 in fifth gear. It needs to be it needs to be clear that whatever we're testing is only what is applied in that forward gear. And then any one-way clutches inside the transmission. Oh, I guess at the end it says engine drivability, because sometimes we use this to torque load the engine to see if we can make a misfire happen. Alright, so here's one of these clutch apply charts, and this is a really useful tool when we're trying to figure out what parts of the transmission may have failed. So which clutches are being tested in reverse? First we want to find reverse, and as we go across, the direct clutch is driving, the low reverse clutch is holding, so that one must have its steel spline to the case, and that's it. So it's just those two are being tested in reverse. So if we have a reverse failure, let's say it was the direct clutch, we may have a customer that says it won't go backwards, and when I go forwards, it makes the first shift, but then the second one, the RPM flares way up, and I can't go anymore, so I have to slow back down until it goes back into second gear. They may not be able to say that, but it might say I have to slow back down until it engages again, or until the transmission does its magic. In the following solenoid operation chart, so these are the different solenoids, and the SSA would be connected to, see, they don't show it on this one, but you'll see it in some of the charts that we're using in the online lab this week. SSA would be also associated with clutch A, so it might say like forward clutch, and then in parentheses A after it, so that means that clutch is being controlled by shift solenoid A. Alright, so in this case, shift solenoid B is stuck hydraulically off. Which gears are available? And it makes the point, which is a good one, on and off refers to the electrical operation of the solenoid, not the actual physical operation. So let's go shift solenoid B. And now we have an interesting thing. We have NL and NH. And if we go down here, normally high is NH, normally low is NL. And what that refers to is So for shift solenoid B, if it is stuck in the, it's saying it's stuck off. Yeah, so if it's in the off position, that means electrically off, that it is going to allow high pressure transmission fluid through it all the time. If it was stuck on, it would be hydraulically closed at that point because it's normally high, so with no current flowing through it, high pressure is applied through that solenoid. All right, so if it was stuck on, then no fluid would flow through it, and the normally low is the way that we would expect it to be. Normally low, if it's stuck off, no fluid flow, no pressure. Stuck on, maximum fluid flow and fluid pressure. Most of these solenoids are what we call variable force, so they can control how much current goes through it with duty cycle, percentage of on time versus off time. So instead of just being on or off, it could be 50% on and 75% on and 30% on, and that just changes shift feel. If we're matting the accelerator, we want that shift solenoid to come on, and to come on with some serious meaning, so closer to 100%. If grandma's headed to the grocery store, then the shift solenoid may only open up 30% because she's putzing along without much torque coming out of the engine, so we can have a slower shift, which is what would occur with a solenoid that's not allowing as much hydraulic fluid and pressure through it. All right, so back to the task at hand. Shift solenoid B is stuck hydraulically off. Which gears are available? You can see our options there. So which ones work when it's off? Reverse would be off, third would be off, fifth would be off. First, second, fourth. I would say that those would all be unavailable, so I think that might actually be a typo in there, which is weird. The following solenoid operation chart, SSB is stuck hydraulically off. Oh, hydraulic. See, I've got myself all confused. So it's stuck hydraulically off, which means that electrically it would be turned on since it's normally high. So that's why first, second, fourth, and sixth would be the ones that work. Pay attention. To 2017 F-150 with a 10R80, so that'd be our 10-speed rear-wheel drive, 800 pound-feet torque capacity transmission. Comes in with shifting concerns. The road test reveals no second, third, fourth, fifth, seventh, ninth, 10th, and second gear manual. Which clutch system will the concern likely be found in? Well, that's a lot of stuff. The fact that it doesn't have second gear and second gear manual may matter. Second gear manual would be our, on the Prindle park reverse neutral drive low, it'd be one of our low gears. So sometimes you have like a manual first, manual second that you can put it into, and that would engage a one-way clutch to give us engine braking. If we're going down a steep hill, like you're headed down Mount Washington and you don't want to burn your brake pads off, then you might be going down in manual first or second, letting engine braking take over, so that just the compression inside the internal combustion engine will slow us down a little bit. So let's see what's on in second gear. Got these for the low one-way clutch there. In third, fourth, fifth, skip sixth. Oh, so that takes the A clutch out, right? Because that's on in sixth, but sixth works somehow for us. I don't know how we got there. Must have had a nice hill to go down or something. Seventh, yeah. Eighth, well, that wasn't even in play to begin with. Ninth. All right, so I think we have our culprit here, which is clutch C. And so all we're doing is just lining up the symptoms with the times that the clutch is applied, and we're looking for those unique instances, like sixth gear and first gear, I guess, for that matter, where if we didn't have first gear, we would know immediately that probably this A clutch was the culprit. Solenoid current and pressure PIDs. So this is just a look at that difference between normally low and normally high. So here we have displayed normally low. So hydraulically off and electrical off are the same. So it's turned off. The ball is in its seat, blocking the fluid flow. It turns on. The solenoid pushes the ball out of its seat against spring pressure. We have fluid flow allowed through it, and these are usually variable force. Oftentimes now it'll tell you whether or not the solenoid's an on-off or a variable force solenoid right there in the specifications when you're looking at the applied charts. And here's just another way of looking at the same thing, whether or not there's pressure allowed to go through. So 1 amp would be 79 psi apparently for this transaxle. I think this is for a 6F50. So like what's in our edge, and what else would have that? Like the Flex would have it, but I don't think that's really a thing anymore. I think the Explorers have a 6F50 in them as well. Well, now they have 8-speed transaxles, but that's a whole different thing. Normally high solenoid current and flow. So in this case, electrically off equals hydraulically on, and hydraulically off is electrically on. So in this case, it's just the opposite of what we were being shown before. When no current flows through it, the solenoid is allowed to open, and when we push current flow into it, it has the spring inside of it, so it pushes up against its own spring, and fluid pressure actually closes that valve. Now, I've never had anyone give me a great explanation for why they would choose the difference between a normally low and a normally high solenoid. The best information I've ever been able to get, and kind of the way that I look at it, is that there is a chance that a transmission may be left without power, right? So like a fuse pops that powers up all of our solenoids, a wiring harness melts, maybe our charging system starts to go bad, and voltage starts to drop below specified limits and whatever. The control module poops its pants, right? All of these are options. So the reason why I think that they have this difference between normally high and normally low is so if we lose power, there's a certain number of solenoids that line up to create a default gear. So this would be a gear that the transmission, without any power supplied to it, would go into. And this gear needs to be able to accomplish two major tasks. One, it'd be great if it let the vehicle go forward. Reverse would be nice, and sometimes that'll work through the manual valve, but forward's kind of the way we like to go most often. So can we go forward that way? Two, can I take off from a stop? Let's say we have a 6-speed transmission and it's stuck in 6th gear. It's going to be really, really hard to take off from a stop, and that's going to create a lot of heat inside the torque converter, because that torque converter is going to need to allow a lot of overrunning to happen inside of it. So a lot of heat would be produced, which could damage the fluid and then potentially damage the internals of the transmission more than maybe they already are. The third thing that it needs to do is allow the vehicle to drive at least some kind of speed. If we're stuck in 1st gear, customers are probably going to blow their engine up, because they're going to have the engine just screaming at thousands of RPM, trying to get off the highway or get out of that dark, scary road that they're on, or whatever. So those are the 3 major things, and the 4th element is just like what's most convenient, what happens to just work out that way when they're designing the transmission. So go forward, take off from a start or from a stop, and also be able to move at a reasonable amount of speed. And we're talking like 20 or 30 miles per hour. This thing's hurt, obviously, so we don't want to be screaming down the road, because there may be other issues that are going on at the same time. But just for people's personal safety, you got to be able to move a vehicle sometime, and if it's physically possible, then the engineers are thinking about ways of making that happen. Normally high, electrically on, hydraulically off, 0 psi. So it's just showing the difference of PID readings there, I guess. Shift timing and ratio PIDs. This is just a screen capture of an IDS recording, and all they're trying to do is show you a few PIDs that could be useful while you're road testing a vehicle. You have shift timing PIDs. How many milliseconds does it take for the shift to occur? It should not take 0. We want it to have a little tiny bit of slippage as it makes the shift, so as not to like snap your head back every time a shift occurs. Shift drop, shift flare. So this is a measurement of either RPM reduction or over revving that happens while a shift occurs, and that's calculations based off of speed sensors. Our gear PID is telling us what gear we're actually commanded to be in. Doesn't mean we're actually in that gear, but it's the gear that the transmission's control module is trying to achieve. And then our ratio PIDs, which kind of work hand in hand with these PIDs here as well. This is the ratio I should have. Did I get that ratio? Yes, the transmission's actually in that ratio. These are just snapshots of when shifts occur, how the RPM is changing. Are we losing or are we gaining RPM? All right, I hope this was helpful, and I definitely hope it helps you out with the certification test, because things are a little bit crazy right now.